Hello, and welcome to this lecture on potential compounds in your LDA-EEG analysis. So in previous videos, we've discussed how classifiers are incredibly powerful techniques. They can easily separate two categories or conditions when univariate analyses fail. They achieve this by finding a difference between the categories and exploiting this difference to tear the two categories apart. But what that difference is often unclear, and this is where the issues arise. This is where the compounds take over. Are the results we look at due to true neural differences between conditions? Or is it a compound in experimental design? Or is it an analytical technique? Or is it even an overinterpretation of the classifier output? Here, I'll discuss these points in turn. First, look at methodological compounds that may lead to spurious results. Then I'll move on to analytical issues that may exacerbate these issues. And lastly, at conceptual misinterpretations of the classifier output. So yes, the first set of these compounds I'm going to talk about are those which arise based on methodology or on paradigm when collecting the to-be classified neural data. These points are something you should consider before you start collecting the data, really, as it's very difficult to address in the analysis stage. So the first issue I'll talk about is block designs. But these issues also extend to designs where the task takes part across multiple sessions on multiple days. A block design experiment is a little bit old school, but in short, it involves presenting a single stimulus type during one block, so perhaps objects, and then in the next block presenting a different type of stimulus. This is a big problem for classifiers because, as discussed before, these classifiers are really powerful techniques that will jump on any difference in the data and exploit it to disentangle categories. And in block designs, a lot can change between two runs. Gel in the EEG cap can dry and affect impedances. Participants can shift positions in the MEG. Participants can get tired. Participants can get accustomed to the task. All of these produce artificial differences in the recording signal that may not reflect differences in neural activity between the decoding of the categories, but nonetheless can be used by the classifier to disentangle the conditions. So what to do about this? Well, it's best just not to use block designs in the first place. Instead, shuffle categories between blocks so there's an even distribution of both stimulus categories across the entire experiment. Again, these methodological compounds that should be addressed prior to data collection and are not analytical compounds addressed during analysis. On a related note, it's important to consider tasks conducted over several sessions. If you have put the participant back in the MEG or you recap the EEG participant, then differences in sensor locations across sessions can impact classification. A classifier trained on one session may not generalize well to another session if the EEG cap or the MEG is positioned differently. Because this is important to balance the exemplars between two sessions, and the same goes for balancing exemplars across blocks. And train the classifier on data taken from both sessions to minimize this source of noise. So try not to separate the stimulus categories in your paradigm, jumble them up so the changes in recordings and behavior that arise over time do not spuriously correlate with your decoding categories. The next compound I'll talk about is correlated variables. So this is something which happens in an event-related design. Whenever you're running any kind of task, the brain is really doing something, one thing, or start that again. Correlated variables, take two. The second methodological compound relates to correlated variables in an event-related design. When running any kind of design, the brain is never really doing just one thing. Rather, it's perceiving incoming information, processing what this information means, and preparing an appropriate response. This is sensing, cogniting, and responding, really. So if you're trying to decode neural representations of incoming information, we need to be aware of what's happening to the signals at the same time when it's being processed and when it's being responded to. Now, it's a strength for classifiers, but it helps amplify the signal and suppress the noise, so it's well suited for tasing apart these processes. However, if these processes are correlated with a particular stimulus category, then this can induce ambiguity into what classifiers are coding. Let's consider the example depicted in the slide. If you have two categories, you have a dog, you have a torch. So This could be an animal and an object category. They elicit different brain activity patterns, and that's what we want to jump into. But they also introduce different response times. So people are quicker to respond to objects than they are to dogs or to animals. So when we run our classifier, it becomes ambiguous whether the classifier is able to pick up on the difference in the neural pattern or the difference in the motor response or the timing of the motor response. So this is problematic, and it becomes very difficult to tease these two apart because of how the classifier works. Well, how do we best address this? Well, really, this involves piloting. You need to make sure in your pilot study that there's no differences between potential compounds such as cognitive engagement or response times between the two conditions you're interested in. If there are differences you see in your pilot data, then you need to adapt the stimuli so that you can attenuate this difference. Doing this before you collect the EEG or MEG data can really help reduce the waste of time and money in the process. Okay, so that's it for the methodological compounds. I will now move on to analytical compounds. Okay, so now I'm going to discuss a few analytical compounds. So these are issues that are introduced based on the approach that's being used, either at the pre-processing stage or during classification. So first one I'm going to talk about is analyzing the weights. So these are the different weightings you might give to channels or to particular features when you're running your classifier, and basically what happens when you try and interpret these weights. So it seems really intuitive to try and look at these weights and see if the classifier is upweighting one part of the data or downweighting another, and then concluding that that weighting, that part of the data, is really important to the classification or not. But you really shouldn't be doing this unless you know exactly what's going on. So I'll try and demonstrate with an example, try and talk you through what's happening. All classifiers essentially act to amplify the signal and minimize the noise. But the recorded EEG at every sensor is most often a blend of meaningful signal and irrelevant noise. You're never going to get a sensor which is perfectly clear, and you're never going to get a sensor which has maybe nothing, particularly with EEG where the signals get smeared so much. So when we use weights, when we use classifiers, we essentially want to maximize the signal and minimize the noise. So let's consider a couple of electrodes. Let's say we've got electrode OZ and electrode FZ. Now, OZ is a combination of the signal we want to pull out and the common noise, which is happening across the skull. So this could be maybe amplifier noise or something to do with reference. It's popping up in everything, or maybe it's a muscle movement or some sort of cognitive process we're not super interested in. You want to get rid of that process. So electrode OZ is the random noise, which always just happens on a single channel, the signal, and some common noise, which is a cognitive process and movement, something with the amplifier. Electrode FZ, on the other hand, doesn't have any aspect of the signal. It only has the random noise and this common noise, this process we're not interested in, this movement, this amplifier issue. So what we can see when we look at OZ is we can kind of see the signal in there. We can kind of see this guy. But we also see a lot of this noise popping up. And then if we kind of look at FZ, then, well, it looks a lot more like the common noise, actually. So we get a lot of this kind of high frequency activity, and we get this little bump popping up there. So what the classifier is going to try and do is going to take these two sources of recording, combine them in such a way that we can maximize their signal while minimizing this noise. So in this very simple example, it's taken as the EEG. So yeah, the weighting, sorry, is taken as this electrode times by the negative of this electrode. So if we look at this, we're not really getting the signal, but if we combine it with the negative of FZ, so that's an inverse of the common noise, we can essentially subtract out the common noise and just keep the raw signal and a little bit of random noise present on OZ. And if we look at this, then it's done a wonderful job of getting us back to the signal. So this weighting of OZ plus the negative of FZ really helps transform this not great representation of the signal into this guy. So it's done a great job, this classifier. But if we now look at the weights, well, we've got OZ plus minus 1 FZ. So the weighting is exactly the same. It's telling us that, hey, OZ and FZ are equally important in terms of the magnitude we're going to weight them. I mean, in the case of FZ, we're just going to inverse it. So we're not going to change the magnitude of the signal, we're just going to flip it, and that's going to help. But so we would come to a conclusion that, hey, OZ and FZ are equally useful, but both contain some part of the signal which really helps us pull out this part. And this is where the fallacy takes place. This is where the issue of analyzing weight comes in. But FZ has nothing to do with the signal of interest whatsoever. It's just a really good way to isolate the common noise which is present in both FZ and OZ without impacting this measurement of the signal. So even though if we looked at the weights, we would think that OZ and FZ are equally important because the magnitude of those weights is both 1, or the absolute of 1. It's actually really not the case. FZ carries no information about the signal at all. It just tells us about some common noise, some common process which we're not interested in. So the short of it really is that you can't just look at these weights. You can't just have a open up the topography and just say, ah, well, it's got a high weighting, therefore it's important, or this one's just been divided by something, or it's tiny, so it's not very important at all. It's much more complicated than that. There are ways to analyze these weights, but we're not going to dive into that today because it's really a whole topic on its own. But yes, so the take-home message, in other words, is just try not to interpret the weights too much. Now, the next potential confound is what we're going to talk about as linear dependence. So in other words, what happens when one feature, e.g. an electrode, what happens when that electrode, that feature can be predicted by another feature. This comes up quite a lot in regression-based analyses under the heading of multicollinearity. And that really means that when two features correlate with one another, it becomes difficult to determine which feature is important and which feature is kind of irrelevant. So, you know, if we try, do we amplify this one electrode A, or do we amplify electrode B? They show the same signal, so but if we upweight both of them, then we kind of, we don't know where the variance is being explained best. And this is quite a problem with EEG analyses. Volume conduction means that the signal captured on a lot of electrodes share a common source, so there's always going to be a lot of correlation between the electrodes. Similarly, electrodes bridged by EEG gel will also have a lot of common signal, and electrodes which have been interpolated because they were not looking good, so you reconstruct them using average signal from its neighbors, are going to share a lot of commonalities with its neighbors because it is literally the linear sum of those neighbors. Even low-pass filter data might show correlations between neighboring time points. So clearly, correlated features can really easily pop up in EEG data. And it's something you might notice with MATLAB error or MATLAB warning when running something like LDA, where you get the message that the matrix is rank deficient, or the matrix is rank deficient to working precision. And this really means that there's some features in the data which are highly correlated. So what can we do about it? Well, one of the best methods to handle this is to try and remove the correlated features. The simplest way to do this would be to just take out one of these correlated electrodes, but it's always difficult to decide which electrodes to take out. So if you have electrode FZ and electrode F1, and they're really highly correlated, then which one would be better to remove? It's kind of an unanswerable question on this. So a more elegant approach is to use a feature reduction method such as principal components analysis, or PCA. PCA moves the data from sensor or electrode space into component space, where these components are maximally independent of one another, and therefore would show no correlation with one another, or the minimum correlation they can possibly show with one another. You can then run the LDA using these components as features, rather than the sensors. And by doing so, you get rid of this linear dependence shared between channels, and hopefully attenuating this potential source of the compound. And we'll move on to yet another issue, and this is overfitting, which has already been covered a little bit in the cross-validation video, so I'm not going to dive deep in here. I'm just going to reiterate the important aspects to consider. So overfitting occurs when you use an overly complex classifier on a small training data set, such as this guy here, where you use a non-linear one on 3 data points. It's got perfect separation, but when you try and apply it to test data, well, then it doesn't seem to work very well at all. In fact, it's you're getting about 40% accuracy, which is worse for chance. So yeah, overfitting is normally what's happening when you've kind of used either too complex a classifier or too few trials on your testing data, your training data, sorry, and then it just doesn't generalize well to the testing data, or it doesn't generalize to a big picture, which has a completely different angle. So when it comes to overfitting, the best way to tackle this is either to use more trials. So that might involve reconsidering how you're doing a cross-validation. So maybe you move from a two-fold approach to a leave one out approach. This will give you many more trials in your training data. Or you choose to go for a more simple approach, a simple classifier. So you don't do non-linear crazy classification, you just stick with a simple LDA linear-based classifier. And hopefully that will help you reduce the chance for you overfitting your data. And then the last compound I'm going to talk about is related to overfitting, but it's when it goes the other way. Sometimes you may choose too simple a model to try and pick out an effect. And if you look at this diagram here, we can see how a linear classifier does quite a nice job at taking apart these yellow and blue stimuli. However, when you try and apply it to a test data, it just doesn't seem to work. All the yellow guys are all over here, so the test accuracy is, you've got these 4 guys, right? But this guy's been misclassified, these 5 have been misclassified. So again, you're doing not too great. And this is what's happening here is that there's actually a much more complex picture going on. There's a non-linear effect where low values or high values on this dimension seem to predict it being yellow, whereas medium values predict it being blue. So here, a non-linear classifier can pull out an effect which a linear classifier cannot. So this is also the case that if you're getting below chance classification, it's maybe a sign that there's some underfitting going on. But as we showed in the previous example, below chance decoding can also be because you're overfitting. And well, this is where it gets difficult to try and tell or diagnose what's going on with the data. Are you underfitting the model or are you overfitting the model? So this is a little bit where you need to kind of just really think about what can be done. Because I'd recommend you try and retest your data without assuming too much. You kind of just want to explore the data. You want to make sure these effects are consistent when you do change the parameters a little bit. If you change your classifier approach, do you still come to the same conclusion? If you change the number of trials in your training conditions, do you still come to the same conclusion? If you change how you partition the data, do you still come to the same conclusion? If they seem to change quite a lot, then it's a sign that there's something going wrong with the fitting, even if it's kind of difficult to diagnose. So if it looks like you're getting some crazy performance, if it's really below chance, then it's really important to just see how it holds up when you reevaluate, change your pre-processing pipeline. Because you may be drawing a false conclusion about your data if you simply just stick with one approach and take the data from there. Okay, so we've talked about methodological compounds, we've talked about analytical compounds. Now what we're going to do is jump on to conceptual compounds. So these are the bits where you misinterpret or overinterpret the outcome of your analyses. So we're going to start off with this issue which has a very unattractive title of A versus B, or is it A versus not B? So in a linear classifier, we're always trying to, or let's give you an example, we have a 2-class linear classifier. We want to tell the difference between animals and objects. And we get our nice little decoding result. It seems to work really well. We're really hitting 80%. We can say reliably that, yeah, we can tell these two categories apart. So what would be the false, or what would be the sort of spurious conclusion, is to say that there's evidence for animals and there's evidence for objects in the data. This is not what successfully decoding the categories is telling you, because in theory the classifier could be pulling out information about it being an animal versus it not being an animal. So in this category, it's not telling us it's an object, it's simply telling us it's not an animal. Or it goes the other way, that we can see that the classifier tells us it's not an object, but it doesn't necessarily pull out and say it's an animal, it just tells us that it's not an object and it is an object. So, and this is maybe a little bit difficult to kind of just get your head around to begin with, but it kind of makes sense that the classifier is pulling apart data based on finding a way to separate the data in 2 different ways. But we assume it's just taking that data apart because it's an animal or because it's an object. But in reality, it could be hundreds of other reasons. We talked about confounding variables, so it might be telling us that there's a difference between these two categories because people respond quicker to animals than they respond to objects. Or there's these cases where the classifier really tells us what an animal looks like. We really, really know, based on EEG activity, what the brain does when it sees an animal. And because when we're looking at torch, the brain is not doing what it's doing when it looks at an animal, we assume it belongs to the other category. We assume it's an object simply because it is not an animal. And this is always just something to bear in mind. It's kind of very easy to conclude that you can get evidence for 2 categories, but that's never really what a binary classifier is showing you. So this is just when you're writing your conclusions, when you're writing out your papers, just remember this little idea that you're never truly showing the difference between 2 categories. You're never really showing the difference between animals and objects. You're simply just showing that these 2 categories can be divided. And then this last confound I'm just going to give you a little bit of a chat about is the idea that just because you can decode something, it doesn't mean that there's a neural representation in the data. So let's say we run our classifier again. This time we're looking at visual stimuli and we're looking at auditory stimuli. And based on neural activity, we can really tell whether someone is listening to a sound or whether they're watching a video. It works really nicely. It's a perfect classifier, just what we love. But just because we can tell these 2 categories apart, it doesn't mean that the classifier is digging in there and pulling out a visual representation, or a neural representation of a visual image or a neural representation of an auditory stimulus. It's simply telling us that these 2 can be apart, can be torn apart, told apart. And this might come about because in certain cases we know that they're explicitly not listening to a category. So if the brain is listening to a sound, then we might expect to see an increase in alpha activity over the visual cortex. The visual cortex shuts down, it starts to idle, it starts to gate information, it starts to inhibit activity. And because there's increased inhibition in this category, in the visual category, then we can say they're not watching a video, therefore they must be listening to a sound. Or at least based on the binary classifier, that's the conclusion made. So in this case, there's been absolutely no representation of auditory signal here when they're listening to a sound. It's simply because we know they're not watching a video, but we know they must be listening to a sound. And in this case, it would mean that we're not actually tapping into a neural representation. We're just tapping into some cognitive operations, side processes which are going on that help tell us about what's happening. So It's a little bit related to our last point of A versus B, because here we've sort of got, we know that in this case they're not watching a video, therefore they must be listening to a sound. So it's sort of not visual, therefore audio, or not audio, therefore visual. And once again, this is just something you need to remember and taper your conclusions accordingly. You just need to remember that just because you can decode something, it doesn't mean you're tapping into the neural representation of that stimulus category. You could simply be tapping into the absence of a different stimulus category. So that's it for this little talk. I hope it's been useful. There's, again, a few more little papers I'd recommend you having a read. The first is just a primer on some different pattern-based approaches. It's focused on fMRI, but they really nicely apply to EEG as well. And they kind of tell you mostly a little about the principles, but also importantly, for this lecture at least, the pitfalls, the issues with some of these pattern-based approaches. And the same can be said for this paper, where they do it with searchlight analyses, another technique used at LDA. And then lastly, we can bring it down to psychiatric imaging data. So all three papers are a great idea just to get how compounds can arise in analysis and how you can be best prepared to tackle those and make sure you don't misinterpret the outcome of your analyses. So thanks for tuning in. See you.